Okay, we have one last question on the Socrative app, and this comes from Wednesday. I don't think we're going to take the whole hour today, but we might. We'll just see. Last one here involves these three models. Now imagine that the fluorines are the white ones on these. This here is your CF4. This here is your SF4. This here is your XEF4. Which one of these is polar? Is it just one of them, none of them, two of them, all three of them? Which one is polar? So check out the models. Here's the XEF4. Here's the SF4. Here's your CF4. Check them out. Let's get an answer logged here, please. And while you're logging that and thinking about that, just want to bring you back to a reminder here on our final exam, Wednesday the 10th. Yeah, that's next week, 7:30. We had a review guide last class period. I might have one or two left. I have two left here, three left. Anybody need one? Did not get one last time? Well, I saw these three hands first. Back here. Maybe I wasn't looking out of my peripheral vision. So, but the review guide is on well, you got it? Okay. So, just to make sure that the number one thing here is we need non-programmable calculators. How many need it again? Just to raise your hand very clearly so make sure I have enough. 1, 2, 3, 4. All right. We're good. I'm also going to be vigilant about things like smartwatches. Anything that looks like a smartwatch can't be used. Okay, so it's going to have to go in your backpack and stuff. No phones out or anything. If I can't tell the difference, just get rid of it so I don't have to ask. Whatever else. Office hours here next week look like this. Again, our final is in this room at S235. This is a time test, which means you don't want to be late. And we do have another class coming in here at 9:40 next week. So we need to get it done, and you do not want to be late for that test. Any questions on the final? All right. Then there's a study session or final exam review session today at 9 o'clock. If you can go, great. If you can't, understand. I'm not going to be there. This is something that is driven by the Academic Support Center and will be located down there. Any questions on that? Okay. Then we were talking about polarity last week, which brings us back to our Socrative app question of the day. And we'll check out the answer here. And we see that the only one that is polar is going to be, how about that? 30, how many percent? 38% of you got it right. Okay, so why is this one not polar? Right, partial positives, partial negatives can't be separated. If you see one that looks like this, where you have an atom in the center, and it's totally surrounded by atoms of a different element, then it's going to be a non-polar molecule. This one here is non-polar because same thing, exactly. We have the central xenon surrounded by like atoms. They're all sitting on the same plane. Now if we look at this and do this with vectors, remember we're going to have vectors that are drawn out to the more electronegative atoms. So what's going to happen to these two? Their effect is going to cancel each other out. The effect of these two will cancel each other out. And since they're all in the same plane, again, they're all going to cancel each other out in that plane. Likewise, all of these angles here, remember what the angles are in this model? 109.5, exactly. So at 109.5, all of these then are basically tugging on electrons with the same force. They're going to cancel each other out. Now you might say, go back to the idea on this one of trying to get all the partial positives, partial negatives on one side. That's actually a strategy that does not work well with this one. This one is probably best answered using vector addition. Okay, so if we use vector addition, what's going to happen to these two here? They're going to cancel out. But how about these two here? They're not going to cancel. They are going to have a net direction like this. As a result, then, these are not going to cancel the effect of these two, and this is going to be a polar molecule. So any questions on this one?
For that, is the central atom the negative atom? Is that right?
Actually, this is sulfur, so sulfur is going to be, can you figure it out for this one? Yes, you can.
Yes, the fluorine.
Yeah, fluorine's the most electronegative atom, so fluorine's going to be the one that's pulling on those electrons the most, and so the direction then that we would use would be to point down towards the fluorines. Okay, anybody else? All right, so with that, one of the questions might be, why should we care? Or what implications might this have? Well, we're going to look at an implication here. Let's very quickly draw out a Lewis diagram for water, which we've done now many times. You should be able to do that one in your sleep. You shouldn't even need to look up the number of electrons on the water. Central atom, of course, on this one is going to be oxygen. And the shape of a water molecule is bent. And then onto the oxygen we're going to have two lone pairs. If we look at the hexane looks like this. We have 6 carbon atoms. 2, 3, 4, 5, 6. And then if we surround all of the carbon atoms with hydrogens, it'll look something like this here. So now if we want to determine the polarity of these, we don't even need to know electronegativities, because hopefully by now you would have learned that water is what type? Polar. And we don't need electronegativities for this one. Based on its shape, this molecule is definitely nonpolar. So turns out that we have a general solubility rule that says this. That general solubility rule says likes dissolve likes. Likes dissolve likes. And what this general solubility rule means is that substances comprised of nonpolar molecules tend to dissolve other substances comprised of nonpolar molecules. Substances made up of polar molecules tend to dissolve other substances made up of polar molecules. And if it's very, very polar, then it turns out it can also dissolve ionic compounds. So what I have up here is I have a couple of burettes, and into the burettes I have placed some water and some hexane. Some water and hexane. And what I'm going to do with these is I'm going to take a balloon and I'm going to rub this balloon in my hair. We're going to place a couple of beakers underneath the burettes, and we're going to watch what happens to this when I rub the balloon in my hair and bring it up to the stream of liquid. So the first one here, and hopefully my hair is dried out enough here. Maybe it has, maybe it hasn't. So I think you can you see the stream of liquid coming down here? Yeah, there we go. So I bring up the balloon to here. Looks like nothing too interesting happening. So we go to this one. And looks like this one's a little off center. There we go. If I bring notice anything happening here? What's happening? Bending. All right, so now as we look at these two here, which one is going to be the water, do you think? Is it this first one or the second one we looked at? Second one. And so that's because water is comprised of polar molecules. And because it's comprised of polar molecules, it's going to have an attraction towards an electrostatic field. And so one of the things we can do with this is one of those demos I like to call my kitchen chemistry demos. This is something you can do with stuff you have at home. If you don't have balloons, you can always do this with a comb. And let's see here if we can stretch this out enough. What you need to do is you can get a thin stream of liquid. So just coming down like this. And then what you can do is you can rub a comb through your hair or a balloon like this. I'm trying to get that. There we go. Then you bring it up to the stream of liquid, and you should be able to see that that liquid, the water, bends towards the balloon. Okay, and again, the reason why it does that is that water is comprised of polar molecules. And so that helps describe some of the attractions that occur between molecules. Unfortunately, that would be great if we can continue on with that in this course. But it's going to be one of your very, very first topics of Chem 2 when you get in there. You're going to talk about intermolecular forces and how molecules wind up attracting each other. But one of the other things we can do here with this is that I can take the two liquids. Remember now that this one here is the water, and this one here is the hexane. I'm going to put some water into here. Now water, if you want to write this down, has a density. Oh, you should know this. What is the density of water approximately? Approximately 1 gram per milliliter. Okay, and for hexane, probably don't know this one. This one is about 0.7 grams per milliliter. So which one is going to float on top? Hexane oil, sure. So now if I have these two, you should be able to see the hexane layer on top of the water here. And I'm going to go ahead and shake these up and try to get them to dissolve each other. And what do we expect to find once I stop shaking?
They will separate again.
They'll separate because hexane is not polar. And so now if we look at the separation, we should see that the hexane layer is going back up here on the top and the water back onto the bottom. So now let's say that one of our goals is to separate substances, and we want to try to pull a non-polar substance out or a polar substance out. What I have up here is some iodine. Now, of course, iodine has a formula of I2. Remember, it's one of our diatomic elements. So if I go ahead and put some of this iodine in here, and I'm picking iodine because it forms a nice purple color when I put it into solution, which layer should the iodine dissolve in? Should go into the hexane. Or at least that's what we think. Let's see if that's true. Remember now, the hexane layer is which one?
The top one.
The top one. So if I shake it up, notice now we're getting the color of the iodine coming out. If I stop shaking this up, we should see here as the layers begin to separate, the iodine is going into the top layer, which is the non-polar hexane. So one of the applications of this might be, now one of the things I like to do is I like to work on cars and engines and stuff like that. And of course, when you go in and work on that stuff, your hands get greasy. And you try to wash that grease off, you put it in water. Of course, what's going to happen to the water when you put it on the grease? All right, it just beads up. It runs off of there because water is polar and grease is non-polar. So you want to get the grease off of there. What do? You use soap. One of the reasons why you use soap, now I don't know if any of you took 1020 in here before, but depending upon the summer that you, or the term that you take 1020, we often do a lab where we make some soap. And in there, it turns out that when you learn about soaps, soaps actually have two different components on them. They have a nice long hydrocarbon tail on one of them, which is non-polar, and they have an ionic end, which is polar. And so if you have the polar piece of the soaps will wind up dissolving into the water, and the nonpolar piece will dissolve into the grease of the oil. And as a result then, it turns out that you can mix together oil and water, and that's really what mayonnaise is. Mayonnaise is an example of something where you take something like oil, mix it with vinegar, which if you put oil and vinegar together, you know that the oil will float on top of the vinegar. But if you go ahead and mix up a little bit of egg yolk in there, egg yolks also contain a little bit of what's called lecithin, which is actually kind of like a soap. It has a polar end and a non-polar end, and that allows them to mix together. And so next semester, again, if you wind up taking the second semester of this course, we'll be talking about intermolecular forces, and you learn a bit more then about how the polarities of molecules work and how they can describe and things such as this and how detergents work and everything. So any questions that you have on the demo here? All right. Last piece we're going to talk about then this semester is going to be on what's called orbital hybridization. Orbital hybridization. Now, you've probably never heard of hybridization before in chemistry. Usually you hear of hybridization where? Probably in genetics. And if you have a hybrid of something, a hybrid is something that contains traits of both parents. Okay? So when we talk about orbitals, we kind of think of a parent orbital, and if we're going to hybridize them, they're going to take on traits of each of the parents, so to speak, that they're made out of. And we're going to start by looking at water. If we drew out a model of water, like we've already seen. Now this wasn't an angle you were supposed to memorize, other than what is greater than or less than, but if you did learn it, what is this angle in here? Approximately about 109.5. It's actually a little bit less than 109.5. This one here is 105 degrees. The 109.5 comes from the tetrahedral structure that we have for arrangement of 4 pairs. Now, part of the problem with a bond angle like this, in fact, if we study anything that has 4 pairs of electrons around a central atom, is that we all see that they're very close to an angle of 109.5. And if we come back then and look at why this is something we should expect or not expect, what we need to do is we need to look first at the orbital diagram for oxygen. And so what we're going to do first is we'll look at the electron configuration for oxygen. If we wrote out the configuration for oxygen, oxygen sits right here, and because it sits right here, that means that the electrons that are going to go in there are going to be these first, which is going to be 1s2. We'll follow it by these, which would be 2s2. And then we end it with these, which would be 2p4. So now, if we drew out the orbital diagram, we're going to look at the orbital diagram for an oxygen atom. If we look at its orbital diagram, we'll have one where we'd show a core of, actually let's not do the core, let's just do the full thing. We'll write out 1s2, 2s2, whoops, we need to put this in the orbital diagram. So we put this in, here's our 1s, then we'll put this in, which is our 2s, and then we have our 2p sublevel. And when we place the electrons into here, we put in 2 here, we put in 2 here, and when we go into the 2p, how are they arranged in the 2p sublevel? One in each, and then we double up. Okay, so once we put that, then we go back and remind ourselves what these 2p orbitals look like. And if you remember what these look like, basically the p orbitals represent this dumbbell shape where the electrons are arranged along an x, y, and z axis. And if you look at any of these orbitals in relation to each other, what is the angle between all of these orbitals? Well, if we compare this one to this one, these are at an angle of 90 degrees to each other. If we compare these two, these are at an angle of 90. If we compare these two, we see that these are at an angle of 90 degrees. So all of the possible orbitals sit at an angle of 90 degrees, but if we come back to the structure of water, we don't see 90 degrees in there, we see 105. And if we looked at something like this, we wouldn't see 90 degrees, we would see an angle of 109.5. So if we were simply trying to say that the way that the hydrogens come in and use these empty orbitals, this can't be the way it is, because if it were this way, we would expect to see bond angles of about 90 degrees. And we don't see that. Instead, what we see, in fact, something like this, which has 4 pairs, all of which are bonding pairs, we see all the angles here are the 109.5. So to explain this, what happens is that these orbitals right here go through a process of hybridization. And so what we say is that these orbitals here hybridize to yield 4 orbitals of equivalent energy. So you recall that S and P's do not have equivalent energy. P's are more complex than the S, which means the P's actually have more energy than the 2S. So once they hybridize, what happens then, if we were to write out their orbital diagram, is something like this. We have the 1s subshell, and then we have 1, 2, 3, 4 orbitals that have this equivalent energy. And we refer to these orbitals as being sp3 hybrid orbitals. Now the label sp3 hybrid orbitals, that is how we come up with sp3, refers to the number of orbitals of each type we use to make up these hybrids. So if we think of it, there's no superscript on this S, so the superscript that's implied is a superscript of 1. What this tells us is that these are made up of 1 s orbital and 3 p orbitals. So in other words, we took 1 s and we took 3 p's and we hybridized them to make these 4 orbitals of equivalent energy. If we had simply hybridized, if the case was that we had used an s and 2 p's, then we would have called them sp2 hybrid orbitals. So the label that we give to them tells us the number of orbitals of each type that is used to make these hybrids. And in terms of their shape, the shapes that we get are something like this. Now if you think of a hybrid, again, a hybrid is something that takes on traits of both parents. And so you notice that one of the traits of an s orbital is it's simply one large lobe. And a p orbital has 2 orbitals, or 2 lobes, each that have equivalent size. So what an sp3 hybrid orbital looks like is something like this. It basically has 1 small lobe and 1 large lobe. And so again, this is what an sp3 hybrid orbital would look like. So again, it has some traits of both pieces. It has this large piece like an S, but it has 2 lobes like a P. And so these are a whole lot like the balloons that we had out here the other day. You might remember then that when we made something like a tetrahedral shape, what we did is we took 4 different balloons, and we said that those balloons represent these orbitals or these electron groups in 3-dimensional space. And so this kind of looks like a balloon. It kind of looks like this small piece here with the large lobe or large piece here. And then if you wind up connecting 4 of these together, so this is one orbital, we'd have a second orbital, third orbital, and a fourth orbital out here in 3-dimensional space. So it'd be like tying together 4 balloons just like we did in here the other day to represent the 4 different orbitals. Then what we do is when we place the electrons in here, we come back and we show the electrons from the 1s, which remain intact. And then we want to show these 6 electrons, which are the valence electrons, and they're going to go into these hybrid orbitals. Now they follow the same rules as before, and that is we place 1 electron into each of the orbitals before we double up. So we put in 1, 2, 3, 4, and then we put in 5, 6, like this here. And then what the rest represent here, these here represent orbitals which are half filled. If they're half filled, what that means is that they can be used for bonding, and we can put in an additional electron here. I'm putting them in with a different color to represent the ones here that come from a hydrogen atom. So what this is here, what this represents is an orbital diagram of oxygen in H2O. So again, this represents an orbital diagram of oxygen in H2O, where these 2 here represent the lone pairs. That is, these right here, these represent the lone pairs, and these 2 here represent the bonding pairs right here. So it basically shows then how we can wind up with this tetrahedral shape. We have the 4 orbitals of equivalent energy, 2 of which are used up as bonding pairs, and 2 which remain as lone pairs. And this is called hybridization. Any questions on this particular model?
So can hybrid orbitals only be composed of the valence shell orbitals?
For us, they can only be comprised of hybrid or the valence shell orbitals, yes. Even in the second semester, we don't look at exceptions to that. If you wind up taking some more advanced inorganic chemistry, then you'll learn that you can sometimes use some inner shell orbitals. But for any of the cases we'll look at this semester, next semester, and probably into your organic chemistry, yes, the only thing we'll look at is hybrid, the valence shell orbitals that can be used.
Okay.
But inner shell ones can be used, and the ones that use inner shells are the transition elements. And the transition element chemistry is typically not a first semester or first year topic. But transition elements do actually use inner shell orbitals. Good question. Anybody else? Okay, then we're going to explain the one that we looked at here to begin with today, SF4. And we want to explain then how in the world we can wind up exceeding the octet rule. So if we look at SF4 and look at its structure, we'll come back to a model that we built the other day. And if we go back to our notes, you can pull out your handout from the other day if you want to look at that. And here's our SF4. Whoops, I don't want to do that. What I want to do is I want to grab this thing. Well, I guess I'll have to redraw it because it won't me to grab it. So we'll put in SF4. We have our central atom, and then we have our, let's see what this was. Fluorine, 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 and fluorine with a wedge here. And it looks something like this. And what we're going to do now is we're going to look at a sulfur atom, and we want to explain how in the world it could have 5 pairs around the central atom, or 5 groups. To do that, we're going to go back and do this one just like we did the H2O. We're going to start by looking at the electron configuration for sulfur. So if we look at the electron configuration for sulfur, we want to get to this point. To get to this point, we're going to put neon in square brackets. And after neon, we take these two, which would be 3s2, and these here, which would be 3p4. So again, we put the neon in square brackets, followed by 3s2 and 3p4. Then we'll look at the orbital diagram of a sulfur atom. If we look at an orbital diagram of a sulfur atom, we'll start with the neon core. And then we'll show the 3s and the 3p subshells. We place electrons like we did before into the orbitals. And we show the 2 orbitals here which remain half filled. Well, now if we look at it strictly like this, what this would tell us is that sulfur really only needs 2 more electrons to fill its outer level. And if we're looking at it only being 2 more electrons to fill its outer level, that would mean that really it could only form 2 bonds, and it's not doing that. So we need an explanation that tells us how we get to this point. And to do that, what we need to remember is that the 3rd level also has available to it some d orbitals. It has a d sublevel. Now in the d sublevel, these orbitals are empty, but they still exist. So again, these orbitals are empty, they still exist. So what happens then is that when sulfur forms these bonds, it actually uses some of these empty d orbitals. Now to figure out how many orbitals hybridize, what you need to do is you need to go back and count the total number of electron groups around the central atom. So how many groups do we have here around the central sulfur? How many electron groups altogether?
5.
There's 5. Remember, this counts as 1, so this is 1, 2, 3, 4, 5. So if we have 5 groups around the central atom, what that tells us is that we're going to have to hybridize a total of 5 orbitals. Back here when we looked at H2O, we had 4 groups around the central atom, and because we had 4 groups around the central atom, that told us we had to hybridize 4 orbitals. So in this case, because we have 5 groups around the central atom, we have to hybridize a total of 5 orbitals. Well, we only have 4 right here, so if we want to make a total of 5 hybrid orbitals, we need to borrow how many d's? We're just going to borrow 1 of the d orbitals. So what we do then is we say that these here, and again the reason why I'm picking out a total of 5 is because we have a total of 5 groups around the central atom here. If there were 6 groups around the central atom, I would hybridize a total of 6 orbitals. So the number that I pick depends upon the number of electron groups around the central atom. So what we say here is that these here will hybridize to yield 5 orbitals of equivalent energy. And once these hybridize, we can then write out an orbital diagram of sulfur in SF4. So to do that, we're going to start with the neon core. And notice now we have, beyond the neon, these now will be the hybrid orbitals. what we're going to do is we're going to show 1, 2, 3, 4, 5 of these hybrid orbitals. And the label we give to them is going to be based on how many we used of each type. So how many S's did we use? Just 1. How many P's did we use? 3. And how many D's? Just 1. So the label we give to this is SP3 d orbitals. And again, they're called sp3d hybrid orbitals because we used 1 S, we used 3 of the p orbitals, and 1 d orbital. If we had used 2 of the d orbitals, if we'd used 2 of these, then we would have called it sp3d2 hybrid orbitals. So the sum of the superscripts, remember ones are implied, the sum of the superscripts is equal to the number of orbitals that were used to hybridize these. Then what we're going to do is we're going to take these valence electrons, which sulfur has how many valence electrons here? 2, 4, 5, 6. So we're going to place those 6 electrons into here, just using the same rules as we did before. So we put in 1, 2, 3, 4, 5, and then we begin doubling up. And once we double up, that leaves how many unfilled or half-filled orbitals here? That leaves 4. And those 4 then can be used to bond with the fluorine. So if we would represent it, again I'm putting these in a different color, I will show these electrons here that tells us that these are the ones that come from the fluorine. And we put in 1, 2, 3, 4. And what this will tell us is that in SF4 we have 1 lone pair, which is right here, and it tells us we have 4 bonding pairs, which are the 4 bonds that we have right here in the SF4. And these hybrid orbitals then are the orbitals of equivalent energy that is used to explain why we can have an excess of an octet, or an excess beyond an octet. So that there is hybrid orbitals. If you were to look at, and I don't remember if I kept all of these up, here we did. I believe I put this in your notes, and by in your notes, this is in your D2L bright space in the content section. This here is what I call the review in a page. This basically summarizes everything from chapter 10 that we've looked at. And so the web address that you'll see up here, don't worry about learning this. This will be in your content section for today in D2L. But it summarizes everything basically we need to know for chapter 10. It tells us all of the possible electron pair arrangements that we have. So again, we looked at them. They were linear, trigonal planar, tetrahedral, and so forth. And then it tells us the number of electron groups, which is 2, 3, 4, 5, and 6 respectively. Again, notice that the number of electron groups that are used. If there's 2 electron groups, we're going to have 2 hybrid orbitals. If there's 3 electron groups, there's going to be 3 hybrid orbitals. When we go all the way up to 6 electron groups around a central atom, then we're going to have a total of 6 hybrid orbitals that are used. And so we sum together those superscripts. Then this here is the number of lone pairs. This is the number of, no, not lone pairs. This would be the bonding groups and lone pairs, and then all of the possible molecular geometries we could have, and then one example of what each one of those winds up looking like. And I'm actually kind of proud of this. This was my sabbatical project a couple years ago where I generated it because students often have trouble with these in 3-dimensional space. We try drawing things in 2 dimensions, and it's hard to realize what they look like in 3. So any questions on this piece here? If I were to review one thing for Chapter 10, I would recommend reviewing this thing right here, because again, this is what I call the review in a page. This collects together everything you should know, with the exception of this last piece here. You need to know this last piece. But any questions on this piece here?
Is it possible to have a total of 12 floor rings?
It is not. No. You pretty much, I mean, this here shows us going up to 6 around a central atom. It is possible to have 7 or 8, but they're way beyond the scope of this course. There's some transition elements that will be able to coordinate up to 8 around a central atom. Okay, anybody else? I thought we were going to get done early, but it looks like we're not. I do apologize, but I am pretty sure you're going to see this on your exam. At least it's often been there in the past. And that is the difference between sigma bonds and pi bonds. All right, here's the difference. First of all, sigma bonds, and these are the Greek letters sigma and pi. A sigma bond is defined as being the first bond between two atoms. While a pi bond is the second and third bond between two atoms. Pi bonds, these here represent an overlap that is along the axis between two atoms. While a pi bond, we say the overlap is on opposite sides of the axis between two atoms. I'm going to illustrate this here with some models. There we go. So to illustrate these, I'm going to show two different substances. One of them is C2H4Cl2. The other one is C2H2Cl2. And to illustrate the difference between sigma and pi bonds and what we mean about the overlap is this. First of all, in a sigma bond, we say that the overlap is along the axis between two atoms. So if these are two different orbitals and they were to overlap along the axis, think of these two red pieces coming together. Now, I can't push them together, but let's say I could push these together. Now, if I could push these together and the overlap is along the axis, one of the features of this is that if I spin it around, the overlap is going to remain in place. Whereas if you get to a pi bond, in a pi bond we say that the overlap is on sides opposite of each other along the axis. So now if I push these together, if these are to overlap and we have the axis between them, the overlap is above and below. What happens if I try twisting these to the overlap? Does the overlap remain intact, or does the overlap get removed? It gets removed. So basically, if we have a sigma bond again is the first bond between two atoms, it's always going to be along the axis. If we have a double bond, the first bond is always going to be a sigma bond, the second bond is going to be a pi bond, and if we have a triple bond, the first bond is going to be a sigma bond, the second and third bond are going to be pi bonds. And so again, it's important to note here that if we have a pi bond, again, the overlap is on opposite sides. So now, what is the implication? Well, if we look at something like C2H4Cl2, that's this one right here. The overlap now occurs right along the axis between the two atoms. Well, one of the features of this is that if I rotate this around, if I were to show the two chlorine atoms on the same side of the molecule, that's the same as showing them on opposite sides. And the reason for that is that constantly in molecules, atoms are in motion. And if they're in motion, writing it like this, where the two are on the same side, is the same as writing it like this, which they are on opposite sides. But if we go to one where we have C2H2Cl2, here we now show the overlap not along the axis, but on sides that are opposite. If I try twisting this now, what happens? Can't do it. Because if I did do it, what's going to happen to it? Bonds are going to break, exactly. So what that means is that in this one, if I show these chlorine atoms on opposite sides of each other, that is different than this one here, where these two chlorines are locked into the same side as each other. They can't twist them around. So these two had the same chemical formula, but a different structure. As a result, we call these isomers of each other. These are isomers. And these are a special type of isomer that we don't have time to cover this semester. This is one of the first topics of your second semester. Connor, I know you had me. Who else had 1020 before? Do you remember the difference between these two types of isomers? Yeah, well, this is important in organic chemistry. When they're on opposite sides of a double bond, these are called trans isomer. And if they're on the same side, these are called a cis isomer. So you'll hear about cis and trans when you get to things like organic chemistry. You might hear something like a trans fat. A trans fat has to do with arrangement of atoms around a double bond. So that's where we're at with everything. That does kind of wrap everything up here for the semester. Any questions on cis and trans or sigma and pi? All right, there is a final exam review session after class on the Academic Support Center. If you're interested, just want to thank you very much for being my students this semester. It has been difficult for me this last half when I picked up extra load, but I appreciate your patience with me.